Is it because, I'm just guessing now, electric force is kind of like, it's not a vector, it's in a 360-degree traction.
The electric force is not a vector?
The electric field is not a vector.
It is a vector.
But isn't it spread around?
It's a vector field.
Vector field.
But electric force is dealing with one charge in the electric field.
No.
It's one direction.
Electric force is weakly charged.
Okay. What's the definition of a force?
Push or pull.
Push or pull. Let's start. So what's the difference between an electric force and an electric field?
There's no push or pull in an electric field.
Well,
The charges are all around it.
It's like pushing all directions.
And in the electric force, there's pushing and pulling between.
yeah, there's pushing and pulling between charges, right?
Yeah. The two electrons.
And this push and pull comes from what we call this environment around the charge. If you have a charge, whether it's positive or negative, there is an area around this charge where if you bring another charge, whether it is positive or negative, that charge is going to experience a force. And the reason it's going to experience a force is because in this area around this charge, there is something called a field. An electric field. We call it a force field. If that field did not exist, this charge would not experience the force. You follow me? So the force comes from that field around the charge. And if this charge is positive, the field points which way? Outward. And so if I bring a charge in this field, let's say right here, I put a charge right there. And let's say that charge is positive. Let's say this charge is positive. This charge will experience a force that will point which way? That way, because this is positive and this is positive. If on the other hand, this charge was negative, then the force would point the other way. Follow me? And let's say this charge was negative instead of positive. Then the field lines would point this way. Vector field that we call an electric field will point the other way. And so if I put the same charge right here, and it's positive, then it's going to experience a force going that way, and if it's negative, it's going to experience a force going the other way. You follow me? So that force comes from the field. So that's what we're doing. We're defining this thing called an electric field. Okay? And the way it is defined is the force exerted on a positive test charge that you bring into that area around that charge. You have a charge sitting there. Okay? And I bring a positive test charge in the area. A positive test charge was somewhere out there. I brought it in. And I put it right there. It's going to experience a force. So in order for me to know the magnitude or the size of the electric field, I measure the electric field with that positive test charge. Okay? And the closer I bring that charge to this charge here, the greater the field. The further away I put it, the less the field. Okay? So the electric field is defined as the force divided by the test charge. This is the Coulomb force that we just studied. This is a Coulomb force. This is the electric field. And this is the test charge. Now, does the test charge have its own field? Does it have a field? So isn't that field going to mess with this field that's already there? How can we solve that problem? How can we solve that problem? We can make that test charge really what? If I make that test charge really small, then the field from the test charge will be insignificant. So whatever field we measure anywhere here will be the field for this charge. You follow me? So it is very important that the test charge be very small. So we don't really care about the test charge. What we care about is the field from this charge right here. And when we do a little bit of manipulation with this, we already know that for this test charge placed right here, let's call it little q, at a distance r, let's call this distance r, from the, let me make this order. The force that it will experience is given by the equation. K, let's call this big Q. Big Q times what?
Small q.
Small q.
For the distance.
Huh?
The distance.
Divided by what?
The distance squared.
Divided by r square. Divided by little q. Right?
Yeah.
And so what happens is these q's cancel. And when that happens, what we're left with is simply K Q over R squared. Now remember, this Q is the source charge. I call it the source charge. This Q generates the field that we're measuring, right? And this R is the distance from the charge. So anywhere out here in space, I can measure the electric field for this charge. All I need to know is the magnitude of this Q, my constant, and how far I am away from that charge. Follow me? So if I ask you to calculate the electric field at some point out here, P, you don't need a charge out there. You just need to know where you want to calculate the electric field. Because the magnitude of the electric field will vary depending on where you are in space. Follow me? That's what this is all about. So today, we're going to learn how to calculate the electric field. And I have some examples for you.